Once we have the Lewis structure, we can predict the shape of our molecules. Like charges are made up of valence electrons are repulsed by one another. They want to get as far away from one another as possible. And we have what's called the valence shell electron pair repulsion theory. Here we have carbon dioxide. We have carbon that's double bonded to each oxygen. And you see the electron domains here, our double bonds, are trying to get away from each other as far as possible. This is a linear molecule, and it has 180 degrees between the bonds. So it has a 180-degree bond angle. Here we have a water molecule. You see the oxygen is bonded to each hydrogen. Now, this is what the molecule looks like. It's a bent molecule. When we take into account the electrons, the lone pairs of electrons here, then we make a different shape. The electron geometry of this molecule is tetrahedral. And that can be seen maybe easier on something like this. So this atom has 4 electron domains, and as it's standing here, it makes a perfect tetrahedral. Here is ammonia. Ammonia is a nitrogen that is bonded to 3 hydrogen atoms. This is the molecule. When we take into account the lone pair on top of the nitrogen atom, ammonia's electron geometry is that of a tetrahedron, but its molecular geometry is called a trigonal pyramid. And here's methane. Methane is a carbon that is attached to 4 hydrogen atoms. Because of valence shell electron pair repulsion theory, those bonds want to get away from each other as far away from each other as possible. So what we have here are bond angles that are 109.5 degrees. This molecule makes a perfect tetrahedron. So this is called a tetrahedral molecule. And you see when all of the possible electron domains are bonds, the electron geometry matches the molecular geometry. When we have lone pairs, the electron geometry is going to be different than the molecular geometry. So we have a linear molecule, 180-degree bond angles. We have a bent molecule. In this bent molecule, the bond angles are going to be a little bit less than 109.5 because the bonds are repulsed more from the lone pairs, than one another. Trigonal planar, again, these bond angles are going to be a little bit less than 109 degrees. So this is a trigonal pyramid. The electron geometry is tetrahedral. And again, when we have all of the electron domains taken up by bonds, what we have is the electron geometry that matches the molecular geometry. But what about our exceptions to the octet rule? When we have something like this is a representation of boron. You see it has 3 places to make bonds. We know that boron only wants to make 3 bonds because it wants 6 electrons instead of the 8. It is an exception. So when we bond boron, we make something that looks like this. This is boron trihydride. And this is a different molecular model kit than this one. Depending on what the lab kit vendor uses, you may see some different model kit representations. So with this is called a trigonal planar molecule. You see all of the atoms are in one plane, and to get away from each other, they make a 120-degree bond angles here. For our expanded octets, when we have 5 electron domains, something like this. So if we have something like phosphorus pentachloride, it would look like this. Now this, with 5 electron domains, this is called a trigonal bipyramid. So these 3 atoms here are in one plane, and then we have 2 poles. So it's a trigonal bipyramid. We have one pyramid on this side and one pyramid on this side. Now, if we take one of those bonds off, and we replace it with a lone pair. Now we have phosphorus tetrachloride. What we have is called a seesaw or a sawhorse molecule. That's the molecular shape. The electron domain or the electron shape is still a trigonal bipyramid. But as soon as we remove one of those bonds and trade it for a lone pair, we change the name of the molecular shape. If I replace two of the bonds with lone pairs, then what I have is called a T-shaped molecule. You can see the T here, but the electron geometry is still trigonal bipyramidal. So if I take off one more bond and replace it with a lone pair of electrons, then I have what looks like a linear molecule. So those bond angles are 180 degrees. Now the other expanded octet example that we have used is 6 electron domains. So something like xenon hexafluoride. This is called an octahedral molecule. So the electron domain or the electron shape of these molecules is going to be called octahedral. And it looks like this. So you have 4 atoms that are in a plane, and these atoms have 90-degree bond angles. And then you have 2 poles. So there's 90-degree bond angles throughout. If we take one of those bonds off and replace it with a lone pair of electrons, the bonds are repulsed more by the lone pair of electrons than they are one another. So they actually bend down just a little bit. Now this is called a square pyramid because you have a square base with a peak. So we go from an octahedral, we take one bond off, then we have a square pyramid. If we take another bond off, it's going to be at the poles. Then we have what's called square planar. You see these bonds are all in a plane. So it just looks like a square. If we take another bond off and replace it with a lone pair of electrons, then we have a T-shaped molecule. And then if we take the final bond off, replace it with a lone pair of electrons, then we have a linear molecule. The electron geometry is still octahedral. You see, we still have electrons in the octahedral positions, but the molecule appears to just If we have a molecule that has multiple what looks like central atoms, and what I'm going to draw out, this is glycine. It's the simplest of the amino acids. So what we have are several atoms that could be called central. We have what is called local geometry. So here my nitrogen is going to have its own geometry, as is this carbon, which is going to be different than this carbon, which is going to be different than the oxygen. So we count our electron domains and we look at each atom individually. So the nitrogen has 4 electron domains. That means an electron domain is either going to be a lone pair or a bond. And so sides of the atom that are taken up by electrons being there. There are 4 places, 3 bonds and 1 pair of electrons. So the electron geometry here is tetrahedral. Let's do this a little more like a chart. The molecular geometry, however, because we have a lone pair of electrons on the top, the molecular geometry is going to be a trigonal pyramid. Now for the first carbon, and that first carbon, I'm just going to have that be aqua. So my first carbon has 4 electron domains. There are 4 places around that atom that have electrons. So that's going to be tetrahedral as well. Now, because all 4 of those places are taken up by bonds, then the molecular geometry is the same as the electron geometry, and it's tetrahedral. The other carbon, the blue one, has 3 electron domains. So 3 sides of the atom are taken up by places where there are electrons. In this case, all 3 of those electrons are bonds. So the molecular geometry is going to be equal to the electron geometry. And this is called trigonal planar. So the electrons orient themselves around that atom to get as far away from one another as possible. And again, because we don't have any lone pairs, the electron geometry is the same as the molecular geometry. For the oxygen that I've highlighted, not that color, for the oxygen that I have highlighted, we have 4 electron domains. Those 4 electron domains make it so that the electron geometry of that oxygen is tetrahedral. Now, because I have 2 lone pairs around that atom, that makes the molecular geometry different than the electron geometry. So that is a bent molecule when we look at it without its lone pairs. When we just look at the bonds and the atom itself, it's bent. Now, what I didn't look at was this one. And I should have picked a different color. And the reason I didn't look at this atom was because it has 3 electron domains. Only one of them is a bond. So as far as molecularly is concerned, that's just going to be linear because we only have 1 bond. But electron domain wise, that's going to be trigonal planar. Now, when we look at these covalent bonds and we have 2 atoms of the same element, they share those electrons equally. And because they share those electrons equally, we call that a pure or non-polar bond. But when we have a bond that has 2 different atoms, they don't share equally. So if we have carbon and chlorine, they aren't going to share equally. In fact, the chlorine is going to pull the electrons away from the carbon. And because of that, this bond is called a polar covalent bond. Now, because chlorine is going to hold on to those electrons more because it has higher electronegativity, we draw what's called a dipole moment. And we show that unequal sharing by drawing an arrow from the positive, the more electropositive atom, and pointing it towards the more electronegative atom. Remember that fluorine is the most electronegative atom, and the trend on the periodic table is as we move up and to the right, we get more electronegative, with fluorine being the most electronegative. So the closer the atom is to fluorine on the periodic table, the more electronegative is expected to be. When we have a molecule like carbon dioxide, which is drawn out like this. Carbon and oxygen do not share these electrons equally. Oxygen will pull those electrons a little further away from carbon and towards itself. Now, we show that with these dipole moments. Now, with something like carbon dioxide, what we have is a linear molecule. And because these oxygen atoms are equal and opposite poles away from carbon, and we have 180-degree bond angles here, these oxygens are pulling equal but opposite. So this is a non-polar molecule that has polar covalent bonds. When we have something like water, and water looks like this, we know water is a bent molecule, but it has tetrahedral electron geometry. The oxygen is going to pull the electrons away from hydrogen, and as it does that, it pulls up towards the electron cloud above the oxygen. So these bonds are polar, but this overall, I'm going to change my colors here, overall this molecule has a dipole moment. This is a polar molecule because those dipole moments all point to the same place and they do not cancel one another out. Ammonia is similar. So we have ammonia. Ammonia is a trigonal pyramid and it has this lone pair of electrons on top. All three of these bonds are polar, and they do point up towards the nitrogen. And there is a cloud of electrons on top of nitrogen, so this is also a polar molecule. Carbon tetrachloride has tetrahedral geometry. There are 4 chlorine atoms, and they each pull the electrons away from carbon. Now, we know from valence shell electron pair repulsion theory that these electrons want to get away from each other as much as possible. So they are equally and oppositely away from one another around the sphere that is carbon. And because although each of these is a polar bond, they're pulling equal and opposite one another, and we have 109.5 degree bond angles in case you care. So this is what's called a canceling shape, and this is a non-polar molecule. So when you have a molecule that its molecular geometry is equal to its electron geometry, and the outside atoms are equivalent, you might have a canceling shape. If you have any lone pairs, you may have a polar molecule, but it may also be a canceling shape. An example of that would be something that has octahedral geometry, octahedral electron geometry, but is square planar in molecular geometry. This would be a canceling shape because each of these bonds pulls equal and opposite away from the xenon, and these electrons are oriented so they are pulling equal and opposite from the xenon.